All right, so we're just going to go over some homework questions. Number 12 on page 25. An airplane is flying at an altitude of 10,000 feet. The airport at which it's scheduled to land is 50 miles away. Find the angle at which the airplane must descend for landing. Did you put the 50 down here? If the airport is 50 miles from the airplane, then it's actually the hypotenuse that's the 50. Okay, so it says, what is the angle at which the airplane must descend? So this is similar to the one we did in class the other day. It's flying straight like this. We're looking for this angle. What does it need to descend at? Which is also this angle because of alternate interior angles, right? So this would be sine of x equals 10,000 over 50. And so you're going to do the second sine, and then 10,000 divided by 50. Okay, so yeah, you're absolutely right. We can't do 10,000 feet and 50 miles. Those two don't gel. So we have to either switch the 10,000 feet into miles or the 50 into feet, 50 miles into feet. Which would you rather do? It's going to be a decimal. Yeah, so let's do 50 miles into feet. So how many feet in a mile? We talked about this the other day. 50 to 80, right? So 5,280. So 50 miles times 5,280 is 264,000. 264,000. Okay, so this equals 264,000. So we need to do opposite, which is 10,000, over hypotenuse, which is 264,000. So on our calculator, we're going to do second sine and then this division. Let's look at it. Second sine 10,000 divided by the last answer. 2.17. 2.17 degrees. Round to the nearest degree, so that would be approximately 2 degrees. Yeah. Mm-hmm. You did? But did but it wasn't 2.17, I bet. It was probably something else that rounded to 2.
No, I got 2.17.
So finding the angles isn't a problem. Finding the sides, we're going to use trigonometry. If we call this x and this y, let's say, we can use either 62 or 28 as our reference angle. But let's stick with 62 since that's the one they gave us. From 62, this side is the opposite. Which color's here? This side is the opposite. This side is the hypotenuse, and this side is the adjacent. So we need to use that 22.8, is that what that says? 22.6? What is it? 0.6? Okay, so we need to use the 22.6 in our calculations because that's the side they gave us. So to get x, I'm going to do opposite over adjacent. That's tangent. Tangent 62 equals 22.6 over x. To get y, I'm going to do opposite over hypotenuse, and that's sine. So sine 62 equals 22.6 over y. And that's the way you'll get those. Now, you do have choices. You could, once you know what x is, well, then you could use adjacent over hypotenuse if you want to find y, right? It's probably more accurate to use what they gave you instead of what you get, just in case you did something wrong on the first one, then you're not blowing your chances for the second one. All right, is that that? Questions on that? Okay. All right, page 27, number 21. This is similar to what we did with the firefighter one, but it's going down to the ground instead of up to a building. Similar, not exact. So we've got Apollo 11 descends to the surface of the moon, but when it's 3 miles up, okay, it measures the angles of depression to each side of this crater. So this angle of depression is 25. That's to the closer point of the crater. Well, remember that if its path is here, that's like the line of sight, that's parallel to the ground. So if this is 25 degrees here, that means this one is 25 degrees here. And then if it's 18 degrees to the further side of the crater, again, alternate interior angles, that makes this one 18 degrees as well. So just like we talked about the other day with the angles of depression or descent or whatever, when you're looking down, a lot of times what you want to do is switch that angle measure into its alternate interior angle so that it's within the triangles you're dealing with. Okay, so here we're going to assume that's a right angle. And so this then is similar to, problems we've had before, where you've got two overlapping right triangles. This is 18 degrees. This is 25 degrees. We know this is 3. Let's call this x and this y. And what we really need is the distance across the crater. That's the y, but we can't get that without getting x first. Besides getting x, we are also going to need, and I recommend just naming this w. The whole length, name it something else. You can call it x plus y. I just find that people get confused with the double variable like that. So if you name the whole bottom something else, like w or z or whatever you want to call it, then you are just doing two tangent calculations. For the smaller triangle, we need tangent of 25 equals 3 over x. And for the bigger triangle, you need tangent of 18 equals 3 over w. Once you know x and w from these calculations, how should we get y? Henry? Yeah, w minus x will get you y. Yeah, makes sense? Okay, so we do have more practice to do with trigonometry, and we will practice that more next week. But I'm going to teach you this last lesson so that we kind of know it all, and then we can sort of practice it all together, okay? So this is called special right triangles. Not that all right triangles aren't special. They are. but some are more special than others. Okay? So these are called 30, 60, 90 triangles and 45, 45, 90 triangles. Okay, and those are directly relating to the angle measures in the two triangles. What makes them special is that they show up a lot. They just naturally show up a lot in, well, you'll see in the unit circle if you, if you end up taking Algebra 2 and pre-calculus and calculus, the unit circle is something that you will get very used to. 30, 60, 90 triangles, 45, 90 triangles make up the unit circle, which is very well used in the next 2 courses, 3 courses maybe. But naturally they also show up in these 2 situations. I'm going to close that. The first situation is if you take a square and you draw the diagonal of a square like this, it cuts that square in half. It cuts it into 2 congruent isosceles right triangles. Yes? See that? Right? Each of these triangles is a right triangle and it's isosceles. What are the degree measures of the angles in an isosceles right triangle? Wesley? Exactly. So we have a 45, 45, 90 triangle when we cut a square in half diagonally. If you look at this equilateral triangle, by the way, what does an equilateral triangle and a square have in common? What do they have in common? Hello? Yeah, all the sides are congruent. All the sides are the same length, right? So we've got basically we have an equilateral quadrilateral, which is a square, and we have an equilateral triangle, right? Okay, if we take an equilateral triangle and we cut this in half, this time we're going to cut it right down the middle. Basically, we're drawing a altitude, which is also an angle bisector, which is also a perpendicular bisector, right? If it's an equilateral triangle, when you draw that one segment, it's all those things. What are the 3 angles in an equilateral triangle equal? What is each angle equal? Each angle. Natalie? 60 degrees. So this angle 60, this angle 60. We just said this is a bisector, so each of these angles is 30. Therefore, we have a 30, 60, 90 triangle formed by, half of an equilateral triangle. Okay, so let's go back to the square. It says here, assume each side of these figures is 8 centimeters. So each side is 8. If I were going to calculate the diagonal of this square, how could I do it? Yep. Yeah, you could do the Pythagorean theorem. You know 2 sides of the triangle. You just need the 3rd side. So you could do Pythagorean theorem. Could we use trigonometry? Yes. But we're going to do Pythagorean theorem instead. It's a D. Okay, so we're going to do 8 squared plus 8 squared equals D squared. So basically we have that the diagonal is the square root of 128. We're going to write this as a simplified radical, not as a decimal. Simplified radical of 128. Well, what is a perfect square Remember the list of perfect squares? 4, 9, 16, 25, etc. What is a perfect square that goes into 128? Okay. 16 does. There's a higher one. There's a hint right here. Henry?
64, right?
64, right. 64 is a perfect square, and we can see it goes in twice, right? So 60 would work, 4 would work, all those would work. But the quickest way to get there is to use the 64. So we're going to do the square root of 64 times the square root of 2, which is 8 root 2. So we started with a square. Each side is 8. Cut it in half diagonally. We have a 45, 45, 90 triangle. Two sides are 8. Diagonal, or the hypotenuse, is 8 root 2. So we've got 8, 8, and 8 root 2. Let's do it again down here with another square. This time each side is 2 centimeters, or whatever it is. We're going to cut it in half diagonally again. And find D. I'm going to let you guys do that. Pythagorean theorem. Calculate what D would. Okay, so you got 2 squared plus 2 squared equals D squared. And that's 4 plus 4 is 8. So we basically have the square root of 8, which is 2 root 2. All right, so let's look for a pattern here. We could keep doing this with all different side lengths, but in this one we have 8, 8, and 8 root 2. In this one we have 2, 2, and 2 root 2. What if I did a square and each side was 5? What would the diagonal be? What do you think? What do you think, Chris? 5 root 2. What if each side was 12? What would the diagonal be? Wesley? 12 root 2. So these are the relationships with the sides of every 45, 45, 90 triangle. Side, side, and then hypotenuse is whatever the side length is times the square root of 2 every time. Okay? Yep.
Like, we get like a 45, 45, 90 triangles, and we already know what the steps are. We just not show anyone can just immediately write like 8 root 2 if we got like something like that with says like 8, 8 on hypotenuse 40, we just write it.
Let's move on to 30, 60, 90 triangles. We cut this equilateral triangle in half. We got a 30, 60, 90 triangle. Again, if we assume each side is 8, like we did on the square, this is 8, this is 8, and this whole side is 8. What would this piece be? 4. All right, so our job in this one is going to be to find the height of the equilateral triangle. So if I redraw the 30, 60, 90 triangle here, I've got 60 down here, I've got 30 up here, this side's 4, this side's 8, this side is my H. How could I find H? Chris? Okay, so let's talk about that, because you're right, you could find this using SOHCAHTOA tangent. If we do that, yeah, or we could use Pythagorean theorem. What is the difference in those answers? If I use trigonometry, could I get my answer as a simplified radical? No. When you use trigonometry, you're going to push that button on your calculator, and it's going to give you a decimal. So you're automatically rounding your answer. You're automatically giving an approximation. You're automatically expressing your answer as a decimal. Okay, so Pythagorean theorem has the benefit of being able to leave our answer as an exact answer. Remember, the difference between exact, well, let's say the opposite of exact is approximate, right? Exact means precisely exactly that value. Approximately means, you took your decimal and you rounded it off. So trigonometry will always give you an approximation. Pythagorean theorem allows you to leave it as a simplified radical, which is an exact answer. So with special right triangles, 45, 45, 90, and 30, 60, 90, we're going to be leaving them as simplified radicals. So we have exact answers. All right, so our preferred method here is going to be Pythagorean theorem. So we're going to do 4 squared plus h squared equals 8 squared. Remember, the c is the hypotenuse. So in this case, 8 is c. So we've got 16 plus h squared equals 64, and h squared equals 48. So we need to simplify the square root of 48. What goes into 48 that is a perfect square? Daphne? 16. So square root of 16, square root of 3. So our height is 4 root 3. All right, let's try that again. This equilateral triangle, again, we're going to split it in half. Each side is 2 of the equilateral triangle. So what's this side down here? 1. And we're still looking for h. 60, 30. Okay, so we've got 1 squared plus h squared equals 2 squared. 1 plus h squared equals 4. H equals the square root of 3. So let's see if we see a pattern here. On our first one, we had 4. Shortest side was 4. Longest side was 8. Height was 4 root 3. Down here we have shortest side is 1. Longest side is 2. Height is essentially 1 times the square root of 3. What if I do, this side is 10. What would this side be? Yep. This side is 16. What's this side? What's this side? See the pattern? Okay, so those are basically the memorized patterns of these special right triangles. And I do mean memorized. We do have to kind of memorize them. Let me show you the next page. In a 45, 45, 90 triangle, I want you to think about labeling these sides based on which angle the side is across from or opposite from, right? So the two sides that are opposite from the 45s, we're going to call them S. S for side. It's not the best variable, I admit it, because sometimes it looks like 5s. But we're going to go with S, okay? Sometimes I try to curl my S a little bit just so that it doesn't look like a 5 as much, but we've got the two shorter sides across from the 45s are S. The hypotenuse, S root 2. In a 30, 60, 90 triangle, we're going to call the side across from the 30-degree angle. Again, the shortest side is going to be your S. This time, the longest side is twice that. Whatever S is, you double it to get the hypotenuse. And then whatever S is, you multiply it by the square root of 3 to get the side that's opposite from the 60-degree angle. Labeling the sides this way is going to be your first step in solving for missing sides of these special right triangles. So it's important to, memorize where these labels go. I like to, for me, I always need a little trick of how to remember stuff when it comes to memorizing. So I always remember that the hypotenuse of both has a 2 in it somewhere. The hypotenuse of both has a 2 in it somewhere. Each triangle has only one side with a radical. So, therefore, when I do 45, 45, 90 triangles, it's never, sorry, I forgot where I left off, but anyway, so each hypotenuse has a 2 in it somewhere. Each triangle only has one side with a radical. Therefore, it's never going to be S, S, and 2S. Right? That would be too easy, S, S, and 2S. It's S, S, and S root 2 for the 45. And then here, you got S, 2S, and then you need a radical, right? And it's not going to be 2 again. It's going to be root 3 this time, so S root 3. So those are just the way I try to remember. All right, this is just real quick. I want you to go through and just label the sides. I know this is basic, but you're just going to get used to where to put the S root 2, where to put the S root 3, etc. The top 3 are 45, 45, 90 triangles. The bottom 3 are 30, 60, 90 triangles. So for 45, we're going to go across from 45 is S. Across from 45 is S. Across from 90 is S root 2. For 30, 60, 90s, we're going to go across from 30 is S. Across from 90 is 2S. And across from 60 is S root 3. So you guys practice that on the other ones with the twisted ones a little bit. Okay, so you should have these labeled like this. Okay, especially look at F. Make sure you have F in the right spots. Sometimes people, when I turn a triangle that way, they think this side is the hypotenuse. But look at 60 degrees. Across from 60 is S root 3. Okay, let's turn the page. I've written out the steps at the top, but we are going to do these 7 problems together to basically learn how to do this. Okay, and you need to kind of bear with me for the first few, because I know that the first few are easy and you don't need to use my method for the first few, but humor me, okay, because we're going to practice the method on the easy ones, and then it's going to become more important on the harder ones to actually follow that method. So we have this 45, 45, 90 triangle. We are going to start by labeling the sides S, S, and S root 2. So we have an S here, an S here, and an S root 2 here. Now, with these problems, there's always going to be one side that they give you a value on, a number. That's the side that I want you to create an equation from. So in other words, I labeled this side S. This side also says 6. I am going to put an equal sign between what I wrote and what they wrote. And so my equation becomes S equals 6. Well, the second step is to solve for S. Well, with this one, that's awfully easy. We already know S is 6. Once you know what S is, you can plug it in to find the other sides. So, X, this side, is just equal to S, and so that equals 6. And then Y equals s times the square root of 2. So we just plug in 6 for s, and we get 6 root 2. So our three sides are 6, 6, and 6 root 2, which makes sense, right? Okay, like I said, I know you probably could have done that one in your head, but humor me. All right, so the next one, again, side across from 30 is s. Across from 60 is s root 3. Hypotenuse is 2s. So put an equal sign between what you wrote and what they wrote. So we basically have s equals 8. Again, this is a nice easy one. S equals 8. We don't really have to solve for anything. That means v, which is s root 3, is going to be 8 root 3. We just plug in s as 8. And u equals 2 times s. So that's 2 times 8, which is 16. So our sides are 8, 8 root 3, and 16. That make sense? Okay. The next one, same process. Side across from 30 is s. Across from 60 is s root 3. Across from 90 is 2s. Put an equal sign between what you wrote and the number they give you. So now our equation is 2s equals 10. Well, now we do have to do a little solving to figure out what s is. What's s going to be? 5, which is the worst case scenario because now s's and 5's looks the same, but that's okay. S equals 5. Well, if s equals 5, we're going to plug in 5 everywhere there's an s. That means y equals 5. And that means x equals 5 root 3. Make sense? All right. D. Side across from 45 is s. Across from 45 is s. Across from 90 is s root 2. Put an equal sign between the value they gave you and what you wrote. You end up with s root 2 equals 8 root 2. How do we solve for s? Algebraically. I know you probably in your mind can do it quickly, but how, technically, how would we solve for s? Chris? You don't want to do that, because then you'll have s squared. If you square both sides, you'll have 2s squared. First, right? We don't want that. Jeffrey? Not subtraction. Only subtract if there's an adding. This is not adding. This is, yeah, we're going to divide. We're going to divide by the square root of 2. Technically, that's what we're doing here. Divide by the square root of 2 on both sides. Well, guess what? They cancel on both sides. So s just equals 8. Which makes sense, right? If s root 2 equals 8 root 2, that means s must be 8. Right? Okay, now anywhere there's an s, you put an 8. That means v equals 8 and u equals 8. Yep. Yep. So your sides are 8, 8, and 8 root 2. All right, so this gets more complicated as we go. Pay attention. All right, part E here. Now we've got side across from 45 is s. Across from 45 is s. Across from 90 is s root 2. Right, s, and s root 2. Put an equal sign between what you wrote and what they wrote as a value. And now we know that S equals 2 root 2. S equals 2 root 2. Anywhere there's an S, we have to fill in 2 root 2. Well, that means when we want to get x equals S root 2. But S is 2 root 2. So we have to change this S into a 2 root 2. So 2 root 2 times root 2 is actually what x equals. Did you follow that? Remember, every line is exactly equal to the line before it. So we're just basically doing the substitution method here. If S is equal to 2 root 2, anywhere there's an S, I can replace it with 2 root 2. Well, x is S root 2. I have to kick out the S and replace it with 2 root 2. That leaves me 2 times root 2 root 2. Well, what is root 2 times root 2? What's root 3,000 times root 3,000? 3,000, right? No calculator, no squaring, square rooting. You don't have to do anything because those two things cancel each other out. So what's root 2 times root 2? 2. Okay, so we've got 2 times 2. So this x is basically 4. So if you notice the side lengths of this special right, one side is 2 root 2, the other side is 2 root 2, hypotenuse is going to be 4. And you'll notice the more you do these, there's these kind of patterns. If the lengths of the s's are whole numbers, like 8 and 8, then the hypotenuse had a radical, 8 root 2. But if the s's have radicals, then usually the hypotenuse ends up a whole number. Not always, but usually. Okay? All right, so let's look at F. Side across from 30 is S. Across from 60 is S root 3. Across from 90 is 2S. Put an equal sign between what you wrote and the value they gave you. So S root 3 equals 18. Well, now we really do have to solve for S. How are we going to get S isolated algebraically? What are we going to do? Chris? Divide by root 3 on both sides. Cancels here. We have S equals 18 over root 3. What's wrong with that picture? Yes, good. We have to rationalize the denominator. You can't keep a radical in the bottom of a fraction. So we have to rationalize the denominator. Multiply top and bottom by root 3. On the top, we get 18 root 3. On the bottom, we get what? 3. Remember, they don't just disappear. People say, oh, they cancel out. No, they don't. They don't cancel out completely and disappear. The radical cancels out, but you still have that whole number 3. So S, in the end, equals 6 root 3. Well, that means D is 6 root 3, right? That side is 6 root 3. F equals 2S, which is 2 times 6 root 3. How do I do 2 times 6 root 3? What's that going to equal? Wesley? Well, it's not really distributing because there's no plus or minus sign. you're really just multiplying 2 times 6 times root 3. And the 2 and the 6 are whole numbers, and the root 3 is not. So can we multiply non-whole numbers with whole numbers? No. So the root 3 actually stays a root 3. Remember I said radicals work a lot like variables. If you had 2 times 6x, what would you get? 12x, right? Same thing here. If you have 2 times 6 root 3, you're going to have 12 root 3. Remember that the shortest side is always half the length of the hypotenuse, right? So it makes sense here that D is 6 root 3 and F is 12 root 3. That's double. All right, and then the other side was 18. All right, so for part G, I'm going to let you try this one on your own. Label the sides S, S, and S root 2. Write an equation, solve for S, and then see what you get as the length of the side. So, just really quickly, I walked around and I saw everybody, I think at this point, has it. So that's S, S, and S root 2. Here's your equation, right? So S root 2 equals 6. Divide both sides by root 2. You end up with rationalizing, and you have 6 root 2 over 2, which can simplify to 3 root 2. So your final answer there, each of the sides of this 45, 45, 90 triangle should be 3 root 2 with the hypotenuse of 6. You are going to start to notice some patterns here. All right, if we turn the page, I just want to do one of these. If you plan to build a path along one diagonal of a square garden, so anytime you have, a problem where there's a square garden or a, here's the square with a diagonal. This one is equilateral triangle. These problems can be solved with Pythagorean theorem, but they also can be solved a lot faster with 30, 60, 90, or 45, 45, 90 triangle. It says you plan to build a path along one diagonal of a 100 by 100 square garden. Leave your answer exact and rounded. Okay, we'll do both. How long will the path be? Well, we could do Pythagorean theorem, but I don't even need to. How long is the path going to be? Lucas? Okay. 100 root 2. Right? You've got a side, and a side is 100 and 100. The diagonal is that times the square root of 2. So the diagonal here equals 100 root 2. Don't even need to calculate anything. This is what you were saying before, right?
Yeah,
don't even need to calculate.
If it's literally just do that.
Just do that, right. Now, though, it does ask for a decimal as well. Well, you still don't need to do Pythagorean theorem or trigonometry. You can just do 100 times the square root of 2, and it will give you the decimal form. That's 141.42. Nearest foot. So 141 point, what did I say? 42? So that's going to be approximately 141 feet. Right? So anytime you have something that fits this description, you can use that method to get your answer. All right, let us turn to okay, so your homework is page 26, 29, and 34. 26 and 29 is more practice with trigonometry. 34 is practicing this 30, 60, 90 stuff. I'm not giving you a lot on 30, 60, 90 because I really want to make sure you're doing it right first before we do much more of it. So you can start that now. Work on whatever you think is the hardest so that I can help you while you're here.